with flow through packed beds? Okay, so any questions from the previous class? Any doubts that you have? Anything that you did not understand? So just to sum up the previous class, what we did was we basically defined a few things in a packed bed, right? We said what is a packed bed, what are the applications where they are used. We talked a little bit about what is called as a packed bed internals. Okay, what does, if you look inside a packed column, what does it have? We talked a little bit about, you know, what are called as liquid distributors, okay, which ensure that, you know, the channeling is kind of minimized, okay, and there are also what are called as liquid collectors, which are basically placed at different locations, you know, across the height of the packed bed. And the job of these liquid collectors is to ensure that, you know, you collect all the liquid that is coming down the packed bed at a particular location, and then feed that into the distributor, and distributor does the job of uniformly distributing the fluid across the cross section of the bed, right? We talked a little bit about different types of distributors as well, something called as a notch type, okay, vein type, you know, and perforated, you know, channels can be used as distributors. Then we went on to talk a little bit about definitions, right? We talked about what is porosity, okay, and then we talked about different ways of manipulating porosity, right? We said you could use packing material of different shapes, you know, in general people use spherical particles or regular particles as packing. Of course, you know, you can go for more complex shapes. We talked about using something called as a Raschig rings, right, and Lessing rings, okay, Paul rings, Burl saddles, you know, things like that, right? And what these different packing gives you is, it gives you a way of manipulating the porosity within the packed bed. It also gives you a, you know, way of manipulating what is the total solid, you know, fluid area that is available for any, you know, process that you are trying to do, okay. Then we talked a little bit about you know, other definitions like sphericity, you know, and we talked about what is the definition, you know, and how does the sphericity depend on different, you know, shaped objects. That's where we had stopped, right? In today's class, what we're going to do is to look at, so we are interested in looking at pressure drop, okay, pressure drop through packed beds, okay. That's what we want to do, you know, for today's class. So that's a schematic of the packed bed, okay. Say that this is a column whose length is like, say, L, okay, and say that, you know, it could be any cross section. So let's say for the simple case, let's take a cylindrical column. Let's say that the, you know, the surface area or the cross sectional area of the channel is something like S0, okay. That's a cross sectional area of the column in which the packing is being placed. Let's write the packing, okay. So the packing is something like this, right? Some spherical particles that are put in a fluid, sorry, that are put in a column, okay, and you want to find out what is the pressure drop through the packed bed, okay. People typically think about two concepts. One is, if I have a way of calculating what is the frictional losses that come because of individual particles in the packed column. If I have a way of calculating that and sum that up for all the particles that form the packed bed, okay, you can come up with a way of finding out what is the frictional losses because of the presence of particles in the column. That's one way of doing it. The other way of doing this is that, you know, actually the liquid is flowing through the column, okay, and it is flowing through the space that is available for it, okay, and basically it essentially flows over the solid surface, right? You have a particles, okay, that form the bed, okay, and there is a space that is available, and when the the liquid is flowing through, it basically flows over a solid surface. Okay, if you have a way of calculating what is the total drag because of the fact that the liquid is flowing over this solid surface, okay, that's another way of thinking about calculating the pressure drop. Okay, so what we're going to do is to look at a very famous model, okay, which is what is called as a channel model. Okay, it's also called as a capillary model for which have been developed to basically predict what is the pressure drop for the flow through the packed bed. Okay, that's what we're going to do. Okay, the concept is fairly simple. So what we're going to do is we're going to say that you have this packed bed, right? Now, if you imagine that the liquid is flowing through this column, and for a minute forget about the particles. Okay, let's say that the liquid is flowing through this column, okay, and of course we said that let's put it this way. Okay, so can I say that, so because of the fact that you have a packed bed, so can I say that the liquid is flowing through some channels? Is that a fair thing to say, right? Because of course, so wherever the liquid is flowing through, so I could, if I were to maybe trace, like let's say I'm going to trace the, okay, so let's say that it was wherever the fluid is flowing through, right? That could be the it could be flowing like that. Can I say that? Of course, it is flowing through the gaps between the particles, right? It is flowing through the gap between the particles, right? And of course, it could so happen that some other stream from some other location may come and join, right? Is it fair to say that? So I can say that the liquid is essentially flowing through a channel. Of course, these channels are not straight channels, right? These are not straight channels, right? These are what are called as tortuous. These are tortuous channels because that's liquid is basically not taking a straight path. Okay, it is basically going through a column which can turn there could be change in the direction of the fluid as the liquid flows through the column. Okay, now the way we are going to work out this channel model is that we are going to say that I am going to replace a complicated packed bed, okay, with a very simple configuration, okay, where I am going to say that there is a channel for the liquid to flow through, and you have the hatched region that I'm drawing. These are the solids that form the packed bed. Okay, of course, it's a very simplified model, right? So all I have to do is I would have to correct for the fact that pipes or channels are not straight. Okay, of course I would have to correct for this thing, but I can assume that for the simplest case that I can say that I can assume a packed bed to be consisting of channels through which the liquid is flowing. Okay, and I'm going to assume that they are straight channels, and of course later on I'm going to correct it for the fact that the the channels are tortuous. Okay, that means they are not straight. Okay, that's what we are going to do. Yeah. Now, whenever you want to do that, okay, so again, one of the concepts that we are going to follow is we are going to go back and look up what we have done in the previous lectures. Okay. Do you all remember this formula? Delta P is equal to sorry, it's not 13, right? It's a 32. Let me just check if that's right. Yeah, remember this formula that you guys had done? What is that? Any thoughts? What is that? What is that? I'm going to write down the name of this equation. Hagen-Poiseuille equation, right? You remember this? Right? So when we looked at flow through conduits, okay, flow through circular pipes, okay, you had developed an expression for, you know, the average velocity through the packed bed. Okay, you had developed expression for what is the pressure drop. Okay, the pressure drop basically goes as 32 times mu, which is the viscosity of the fluid, okay, which is flowing through the conduit, and V bar is what is called as a average velocity with which the liquid is flowing through the column, and D is the diameter of the column through which the liquid is flowing, right? Whenever you want to kind of look at analogy, okay, of flow between, you know, pipes of different dimensions or different kinds, what you do is you would have to come up with a way of actually relating the parameter that you that are involved to the actual quantities in a particular flow problem. Okay, so for example, say that you have flow through a circular pipe. Okay, say that I would like to use whatever equations that you have developed for a flow through a circular pipe. If you want to extend that to flow through a rectangular channel. Okay, so one of the concepts that people do is they, instead of so wherever you have dimension d, which is the diameter of the column, they replace that with what is called as a equivalent diameter. Okay, you replace d, which is the dimensions of the pipe through which the liquid is flowing through, in this case, to what is called as an equivalent diameter. Okay, that's one thing you have to worry about. And this V bar is the average velocity with which the liquid is flowing through the pipe. Okay, in the case of packed bed, we said that there's something called as a V0 bar, which is what is called as a superficial velocity or the empty tower velocity. That is the velocity before the liquid enters the column. Accordingly, the velocity with which the liquid is flowing through the column is V0 bar by epsilon, right? That's the actual velocity, right? So therefore, what I'm going to do is I'm going to take this expression that has been developed for pressure drop for flow through pipes, and we know that this is only valid for laminar flow conditions. Okay, I'm going to use that, I'm going to modify it, and then somebody has a question? Yeah. What's that? Oh yeah, delta P by L, I'm sorry about that. Yeah, that's true, right? So this is delta P by L, that is the pressure drop per unit length, right? That is equal to 32 mu V bar divided by D square, right? Yeah, that's right. Okay. Now, how do we go about calculating the equivalent diameter? So if you have a simple geometry like going from a circular pipe to a square conduit or rectangular conduit, you can, there are simple ways of getting what is the equivalent diameter, but however for this case it's a little bit complicated, right? What do you think that one should be doing to get what is the equivalent diameter? So I'm just going to say that the length of the tubes is same as the length of the packed bed, and I'm going to say that this diameter of the pipe through which the liquid is flowing through is, say, D equivalent. Okay. So what do we do? So for doing that, we do two things. Okay, one is we do what is called as a surface area balance. Okay, and number two, what is called as a volume balance. Okay. Now let us say that there are n conduits, okay, or n tubes through which the fluid is flowing, right? And let us say that the diameter of each of tube is D equivalent. Okay, can I write an expression for the total surface area of all the tubes that make up the column, that make up the packed bed? Okay, that is total surface area of all the channels or tubes or capillaries that make up the packed bed. What will that be? That's going to be n times pi D equivalent times L. Is that okay? Because you have tubes, okay, your perimeter, right, times the length, okay, is going to give me what is the total surface area that is available for the fluid to flow through. That multiplied by n is going to give me what is the total surface area of all the channels put together. Is that okay? Yeah. Now, okay, let's think about expressing what can you say about the volume of the solid particles that are present in the packed bed? What can I say about the volume of the, okay, let me just go back here, okay. What is the volume of solid particles in the column? Okay, what is that? It's going to be S naught, which is the cross sectional area, times L, that's going to give me the volume of the packed bed, okay, that multiplied by 1 minus epsilon is going to give me the volume of the solids in the, is that okay? That is going to give me what is the total volume of all the solid particles that you have in the packed bed. Now if I divide this, right, you have a doubt? Somebody has a doubt? If I divide this by Vp, which is the volume of the single particle, what is it going to give me? It's going to give me the number of particles, right? It's going to give me the number of particles that are present in the bed. Is that okay? So now if I ask you what is the total surface area of all the particles in the bed, okay, is S naught into L into 1 minus epsilon divided by Vp multiplied by Sp, right, where Sp is the surface area of every particle that you have. Is it okay? Now, you know that when we talk about sphericity phi s, right, it is 6 by dp divided by sp by vp, right, that is a definition of sphericity. Okay. Therefore, I can write this sp by vp as 6 by phi s into dp. Okay. I can substitute here S naught into L into 1 minus epsilon multiplied by 6 by phi s into dp, right. Yeah. Okay. Now, the fact that you know the channels are basically made up of the walls, right. So, you have these channels, right, these channels through which the liquid is flowing. Okay. Now, the fact that these channels are basically made up of the walls that arise because of the particles present in the fluid. Okay. So, what I am going to do is I am going to say that the total surface area of all the channels in the column is equal to the total surface area of all the particles that I have in the system. Okay. Therefore, what I can do is I can write n times pi d equivalent times L, okay, that is the total surface area of all the channels in the column is equal to S naught into L into 1 minus epsilon into 6 by phi s into dp, that is the total surface area of all the particles that I have in the column. Okay. Therefore, this is basically the surface area balance. Okay. All I am doing is I am calculating what is the total surface area of all the columns that I have in the system, and that has to be equal to the total surface area of all the particles in the system. Okay. This equation is, yeah, if you have any doubts we can discuss that. The only ideally there is some small correction as well, right, because what is happening is that if you have particles that are in contact, right, there is a small contact area that is available. I am basically neglecting that. Okay. But if you leave that, if you assume that these are point contacts, if you assume that there is no significant reduction in the surface area because of these contacts, this is a good equation or a good approximation to say that the total surface area of all the columns that you have in the in the bed is equal to the total surface area of all the particles that you have in the column, right. Is that okay? Right. All that we did in obtaining this right hand side was that we said that the total volume of the bed, okay, that or the total volume of the particles in the bed is S naught into L into 1 minus epsilon. Epsilon is the void fraction, right, that gives me the total volume of the solid divided by the volume of the particles will give me the number of particles in the bed multiplied by Sp, which is the surface area of every particle, that basically gives me the total surface area, and all we are saying is the total surface area because of the column and should be equal to the total surface area of the all the particles, right. Yeah. No, this Sp by Vp, okay, this is, we know that this is a characteristic of the particle that we are using, right. Okay. What is that? Oh, dp is basically the diameter of the particle, right. If you have a packed column, okay, if I am saying that I have particle of some dimension, okay, if I were to be working with spherical particles, if I say that your diameter of the particle is dp, okay, that's the dp here, okay, that is the diameter of the particle that make up the column, that's dp. No, the fact that I'm using sphericity concept, it need not be for a spherical particle, right? It could be for any particle as long as the dimensions of the particle is dp. That's all. Okay. Yeah. I mean, all we are trying to do is, so if I take this to be for a spherical particle, we know that it is basically 6 by dp itself, right? But however, your sp by vp, which is 6 by phi s into dp, okay, is going to be just 6 by dp for the case of spherical particle. However, if you're working with particle of any other dimension, you would have to work with having this prefactor, which is sphericity. Okay, that's all. Yeah. Now what we'll do is we will look at the volume balance. Okay. Okay. Now what we're going to do is we're going to say that we talked about the total surface area that is available for the liquid to flow, right? What about the total volume of all the conduits put together? What is the volume of all the conduits put together? That's going to be equal to n times, right, d equivalent square into pi divided by 4. That is, that's the right, multiplied by your L. Okay, right? That's the total volume of, so that's the volume of the cylinder, right? Your pi d equivalent square divided by 4 multiplied by L is going to be the volume of the pipes itself, multiplied by n, which is the number of pipes that I have. That basically is the total volume of all the conduits put together, right? And of course that has to be equal to the total volume of the liquid that you have in the system, right? That's going to be S naught into L into epsilon, right? S naught is your cross sectional area, L is your length, and epsilon is the porosity. Okay, and this is the volume balance. Okay, all that we are doing is we are saying that the total volume of the liquid, in the system, okay, or the liquid that is flowing through the system is basically equal to the volume that is available for them to flow. In this case, the total volume that is available for them to flow is going to be the number of channels multiplied by the volume of each channel, right? Okay. Now what you're going to do is you're going to use this equation, okay, and the equation that we wrote up here, okay, that's 1 and 2. You're going to use that and you're going to work out and then get what is your D equivalent. Okay, so let's do that. Okay, so n times pi D equivalent times L was equal to S naught into L into 1 minus epsilon divided by phi s into dp into 6, right? Something like that. That's your, yeah. Okay, can you work with 1 and 2 and let me know what is your D equivalent? Can you do it in your notebook? Tell me what is the D equivalent. Okay, so what you can do is I have this equation that relates this volume balance, right? What I can do is I can substitute for n from equation 1. Okay, I can substitute for n from equation 1. So what I have done is, so n I'm going to write it as, okay, S naught into L into 1 minus epsilon into 6 divided by phi s into dp multiply, okay, I have, right, yeah, okay, divided by pi into d equivalent into L, right, that's your n, right, multiplied by, you have this term, okay, that is pi t equivalent square divided by 4 into L should be equal to S naught into L into epsilon. So S naught L gets cancelled on both the sides, right? So if you work it out, it turns out that, you know, your, this is D equivalent, it turns out that, you know, your D equivalent is going to be 2 by 3rd into phi s into dp into epsilon divided by 1 minus epsilon. Okay, you can work it out, right? Therefore, your D equivalent is 2 by 3 into phi s into dp into epsilon divided by 1 minus epsilon. Okay. So you've been able to get hold of a expression for D equivalent, which I can further use and then substitute in the Hagen-Poiseuille equation and calculate what is the pressure drop, right? So let's go back to that equation, right? So your delta P by L was equal to 32 mu V bar divided by D, now D equivalent square, right? Can you substitute for D equivalent square and then just, okay. So what is done is that, you know, so we, of course, we said that, you know, this is actually applicable only for straight conduits, right, or the straight pipes. So because of the fact that, you know, your channels are not straight, you would have to introduce a factor called lambda, lambda 1, which is what is called as a tortuosity factor. Okay, so therefore I'm going to multiply this everything by lambda 1. Lambda 1 is a parameter which is called as a tortuosity factor. This basically takes into account the fact that the pipes are not straight, okay, they are tortuous in nature, okay, and there are, we're going to, people have done experiments to determine what this lambda is. We'll talk a little bit about that in the, you know, in the next few minutes, okay. As mu, and of course this is not going to be is V bar, okay, I would have to replace that by V naught divided by epsilon, right, that's your, the average velocity, right, and I would have to substitute for what is D equivalent, okay. So what you can do is, that is 2 by 3 into phi s dp square into epsilon divided by 1 minus epsilon, right, that's your not ds square, right, that's just a dp, right, and of course there's a lambda 1, that is the tortuosity factor, okay. So if you work it out, what you actually get is something like this. You get 72 times lambda 1 times V naught bar times mu into 1 minus epsilon square divided by epsilon cube into phi s square into a dp square, okay. Yeah, that's what you're going to get, okay. All that you've done is you basically simplified it further, right, okay. You substitute for what is D equivalent in terms of 2 by 3 phi s dp into epsilon divided by 1 minus epsilon square, because you have one epsilon, that epsilon square here, and there's one epsilon here, so therefore you have this epsilon cube with the denominator, and of course you have phi s square into dp square, okay, and mu and V naught bar that comes from here, right, and 1 minus epsilon square that comes because of the fact that you have 1 minus epsilon in the denominator, right, and of course if you work it out, so that's going to be your 72 times lambda 1, okay. And what people have done is, they have done experiments in which they have a way, that's delta P by L, right. If you take columns of, you know, in which you maintain different delta P's, you know, and then you vary your delta P by L, or if you take columns where you keep your delta P constant, and if you vary L, right, you vary this, okay. When people have done a lot of experiments by using packed beds of different materials, and they've kind of found that this 72 times the lambda 1, okay, which is the prefactor, it apparently it's about 150, okay, which leads to lambda 1 of the order of 2.1, okay. And this 2.1 so one way to think about this is what's called the tortuosity factor. One way to think about this would be that the fact that the channels are not straight, okay, of course the fluid is going to spend more time in the packed bed, okay, because it has to pass through a greater length of the tube, okay. And the fact that this is slightly greater than 1, it tells you that of course they are tortuous, okay. And you can think about this being the typical time that the fluid spends in the column would be roughly of about 2 times what it would spend if the channels are straight, okay. This is roughly is what you can say, okay. And of course this depends on the kind of flow conditions, okay. So far what we have done is we have assumed Hagen-Poiseuille equation, which is valid only for laminar flow conditions, okay. So now similarly what we are going to do is we are going to develop a similar expression for the case where you have a turbulent flow condition, okay. Can we do that? Any doubts with this? So this tortuosity factor, there is no way of directly measuring what it is, okay. The only thing that you can do is you formulate the problem in such a way that you are under this laminar flow conditions, that is your Reynolds number is less than 1, okay, for the flow through packed bed problems, right. And then what you do is you carry out experiments. If you have a way of measuring delta P, okay, and if you have a way of varying say V naught bar, okay, if I know what is epsilon and your dP and everything, therefore what you do is if you were to plot how this delta P by L varies as a function of V naught bar, okay, what you would do is you would get a straight line that is passing through the origin, right, and from the slope they basically back calculated what this lambda 1 is, okay. That's how it is done, okay. And this is based on a set of experiments done on columns of different packing material, different length columns and stuff like that, okay. And this tells you something about lambda tells you something about how tortuous the channels are, okay. It turns out that the lambda that you get for this case is 2.1, and however if you go to the turbulent condition, the lambda that you get is much higher, okay. It's of the order of something like 68 or something like that, okay. We look that number a little later, okay. Therefore, okay, this lambda 1 correction is necessary because of the fact that the flow is not through straight channels, okay. Any questions? So it's almost time up. We'll stop here. So I'll take a few questions if you have some, okay. We'll continue with doing something very similar for the cases under which your flow through the tubes are under laminar flow conditions, okay. Any questions? You have a question? Both of you? Yeah, yes. You have any questions? Yeah. You can tell me. I mean, let's discuss that. No, I mean, if you have any question that you have, you should just raise, and then we'll figure out a way to, understand that. No. Okay. Is the concept clear of the capillary model or the channel model? It's a simple concept that you're basically assuming that the flow through packed bed indeed can be thought in terms of flow through channels, okay. Of course these channels are not straight, okay. There are going to be different streams joining from different locations of the packed bed, okay. However, for the sake of simplicity, we assume that there are straight channels. We said that there are n channels of exactly the same length as the length of the packed bed, and we did very simple volume balance and the surface area balance. That gave us a way of estimating what is the equivalent diameter, okay, or you can think about this as a equivalent diameter of the conduits through which the fluid is flowing, okay. And then we substituted that in the Hagen-Poiseuille equation, and then came up with the expression for what is the pressure drop through the packed bed, okay. It turns out to be 150 times mu naught v naught bar into mu 1 minus epsilon square divided by epsilon cube into phi s square into dp square. Okay, that's where we stop here today. Then we'll continue with it tomorrow.